Some backstory. One of the first talks I ever heard in this building, in this room, was by Carlos, 10
years ago. Yep.
Carlos Gershenson is a professor at the SUNY Binghamton, which has a wonderful complex system science, network science group there. I was delighted when I saw this title. I was intrigued. And so I think I'll say nothing else.
Yeah. Thank you, Brian, for organizing. Thank you all for coming. So let me try to go here and try to see my notes, which now. Yeah. So this part of a larger project that, oh, there you are. Yeah. Thanks.
Everything good?
Perfect. So, I mean, naturally, we have aversion to errors in the sense that we are taught since we're kids that it's wrong to make mistakes. And it's natural evolutionary because usually when we make errors that can be harmful or deadly for us or other members of our species, and we can actually see the evolution of our culture as an increase of environmental control, so that we can increase our chances of survival. And this has led us precisely to develop science and engineering in such a way that we can predict everything that goes around us so that we can avoid things that can be harmful or undesirable. However, the question is, well, how much can we control, especially when the possibility to control much of our environment can have undesired consequences. Let's say it is true that never has been such a great control over our environment, which increased life expectancy, but at the same time, having such a big control means that if we make mistakes, their consequences are much larger. Like if there's oil spill or nuclear spillover or whatever, then it has consequences that before our species wasn't able to do. So actually, if we ask how much of our environment we can control, we don't know, but we should be able to know. So this talk is part of a larger research program that tries to systematize limits of science, which of course is very ambitious and long-term, but let's say I'll try to invite you to contribute to this. So a bit of history in ancient Greece. I mean, if you remember Pythagoras' theorem, it was known that say the length of the hypotenuse of a square triangle should be square root of 2, but they didn't have irrational numbers. So actually, they kind of ignored that they couldn't represent this number. Also because Greek geometry worked more with ratios rather than numbers. But the thing is that it was only until the late 19th century that Georg Cantor defined the infinitesimals that we had the concept of irrational number. And before, let's say that was a limit of mathematics, but then we were able to overcome it. However, not all limits are, let's say, just waiting to be extended, but there are some inherent limits. And one example where Cantor was also involved has to do with formal systems. So Cantor, when he developed set theory, he identified paradoxes that made many mathematicians uncomfortable. So for example, he showed that the natural numbers can contain themselves an infinite number of times. So if you go into a subset of an infinite set, you will find the same cardinality of that set, and things that were deeply disturbing for conservative mathematicians like Poincaré and his own advisor was sabotaging him so that he will get a position in a decent university. So he ended up in Aachen or somewhere there. And he was accused of being a corrupter of youth and well, many different adjectives. However, Hilbert and Russell kind of saw that he was on the right track. Russell, his Principia Mathematica, was trying to solve these paradoxes, was not successful. Later, Hilbert defined, let's say, his program was trying to prove that mathematics was complete and consistent and decidable. And Gödel showed that, let's say, for not only mathematics, but all formal systems that have enough complexity are incomplete and inconsistent. The only one who understood this at first was von Neumann, because he was PhD of Hilbert and he was working precisely on this problem. And later Turing showed that also formal systems are not decidable. And later Chaitin kind of complemented by proving also some other limits of mathematics. And of course, we wanted mathematics to be perfect, and we want people to be perfect because we don't want to make mistakes. We want our machines to be perfect, but is that even possible? Well, no, it's not possible. I mean, it's formally proven that math cannot be perfect in this way, but I think it's better in this way, and I will tell you how. So, I mean, let me start speaking a bit artificial intelligence. Alan Turing said in 1948, if a machine is expected to be infallible, it can also be intelligent. And he was referring that in many cases, we learn from our mistakes. So if we want machines not to make mistakes, they won't be able to adapt. And imagine if we lived in a world where actually there would be consistency and completeness and decidability, then there wouldn't be able to be novelty. So evolution wouldn't be possible. If we want evolution, then we need incompleteness and inconsistency and non-decidability. By definition, novelty cannot be predicted. So there should be limits for predictability. And in artificial intelligence, there are limits related to meaning, to artificial general intelligence. That's I won't go into them, but with some colleagues and a PhD student, we have worked on the limits of classifiability. So let's say the details are in this paper, but in summary, it's if you have two classes and they overlap, then you cannot have perfect classification. No matter how much data you have, smart are your algorithms, there will always be errors. So then what do we do? Well, one step is to measure how classifiable data sets are, because if we require a certain efficiency or efficacy and the classifiability of data set is lower than that, then we need to find a completely different solution before we start programming or gathering data. And I mean, there are many other problems related to artificial intelligence, and let's say this a list of limits on science. So predictability, computability, classifiability, optimizability, and so on and so on and so on. But let's try to speak about networks after this brief introduction. So what do you think? Are networks real?
No.
Why?
So why are we in science?
Well, of course, it depends what we define reality. There are many definitions of reality. But let's say it's a big discussion, but it's also related on how much do we know and how do we get to know. And in science, we use models, and these are also limited. I mean, there's this phrase of George Box that all models are wrong, but some are useful. We can say that, of course, models are not true, but then they can tell us something about the world. And in philosophy of science, there's lots that has been said on the matter. Of course, we need to reach a balance between how much detail we put in our models and how simple they are. We want to predict as much as possible, but being concise as possible. And from Silvia and Bruno concluded, Lewis Carroll has this story of, let's say, cartographers that make maps so detailed that then they're scale 1 to 1, and then it's, let's say, not very useful. Or in this short tale by Borges, that's the full story. It's basically, it says the same thing. And basically, if a map is just the same as the phenomena it's trying to model, then it's not very useful. By definition, models are simplifying. But then how much do we simplify? It's always a trade-off between how much information we have, how much we want to predict, and how much can we predict. And this has also been used by Baudrillard in the sense that, let's say, he puts the example of Disneyland, of something that's not real, but then we know that we invented it, but then we take it as the real thing. And also, this tells us that if we simply have a model as complex as the phenomena, then it's not giving us any more information. So by definition, models need to be simplifying, but then how much simplifying, it's very contextual. And we can have different types of model depending on their substrates, so material, organismal, formal, computational, conceptual. And how sophisticated models should be, how many details do we need to put into them, at which scale do we need to model, or which scales. And also there are different types of model depending on the purpose. So in many cases, we assume that models should be predictive, but then there are also explanatory models. So they can be highly simplifying. And of course, the amount of detail that we need in a predictive model is much higher than in an explanatory model, and so on. There are many things that we can do with models. But let's say, if we need to use models to study reality or phenomena, how can we have access to reality, let's say, if it's just with our description? And in philosophy, there's this distinction between epistemology and ontology. So epistemology is the study of knowledge, how we get to know our world. And ontology tries to describe the world itself independently of an observer. So it's a bit like this subjectivity and this subjectivity. But let's say we cannot even speak about what's real if it's not with language. And the moment that we use language, it already becomes subjective because every word is simplifying the richness of the things themselves. But also, we cannot have an epistemology without an ontology, because otherwise we need something to ground, and then, let's say, it would be almost arbitrary what we have. And Schrödinger wrote, "The world is given to me only once, not one existing and one perceived. Subject and object are only one. The barrier between them cannot be said to have broken down as a result of recent experience in the physical sciences, for this barrier does not exist." So this idea is present in several Eastern philosophies, that you cannot distinguish between subject and object and action of perceiving, because you cannot have one without the other. So, of course, philosophically, it might be satisfying, this answer, but in practice, we would like to know and quantify how much can we know, let's say, given these restrictions. And related questions are interactions real? I mean, networks are supposed to be useful for modeling interactions, but one view of what reality is that comes from classical physics is that if it's made of matter and energy, it's real, and if not, it's epiphenomenon. But then interactions are neither matter or energy. Are they real? And then reductionist physics would say no, it's just epiphenomenon. But, well, it depends, because there's a quote from Feynman that he says that matter is interactions, because you cannot get A is made out of B or B is out of A, or matter is interaction. In the sense that you cannot have isolated matter. The way that you detect any particle is because it's interacting with other particles. So there are other examples that might be easier to understand. So one of them is money, because the value of money is not, let's say, in bills or in gold or whatever we want to give value, or in bits where we store our savings. Because of course, the bills can lose the value very quickly, or stocks can change their value, or the value of art can vary wildly. However, money has causal effects on the physical world, and one example is this building. Without money, the matter that makes these walls wouldn't have been able to be transformed from wherever it was before to where it is now. So let's say we wouldn't be able to predict that transformation of matter if it wasn't because of money. So we can say that interactions or information that carries the value of money has a causal effect on matter and energy. And interactions have been studied scientifically within complex systems. And I mean, in this paper, I describe some implications of considering interactions as real. And of course, they're easily represented with networks. But what we know is that in general, the more interactions we have in a system, there will be more change, and then that reduces our predictability. And this classic relationship from structure to function. If we have higher connectivity, then usually the function will be less predictable. And it's, let's say, usually represented in terms of order of chaos, and somewhere in between you have balance that can be called criticality or complexity or other things you choose. And interactions limit predictability. One way in which it does it is because interactions can generate new information that is not in initial or boundary conditions. So, example of elementary cellular automata, let's say you have an initial state, very simple rules, it's predictable, no noise, but still you cannot predict the future pattern if you don't go through all the intermediate time steps. So this is known as computational irreducibility and limits our prediction. And also interactions can generate information that will change our problem domain. So in optimization, this is known as non-stationarity. And in many cases, this generates states that will never be repeated and that have never been visited. So this will limit our prediction. And one way of going beyond this limit is with adaptation. And let's say this has been studied from cybernetics, with artificial life, in cognitive science as well, how the different systems can adapt to unforeseen changes in their environment. And another limit that we have in complex systems is understanding emergence, which, let's say, we can understand it as properties that are at one scale but not at another. One example, with carbon atoms, we can know everything about carbon atoms, but then depending on their structure, on their interaction, on their organization, we can have the same components making diamonds, graphite, nanotubes, buckyballs, and the material properties of these materials vary widely, but they are composed of the same elements. It just depends on how they're organized. So, I mean, there's nothing spooky about this. It's just that you cannot deduce the properties of the material based on the properties of the atoms. You need to consider their interactions. And there are many flavors of emergence, and the ones that, let's say, are problematic are in red: strong emergence that implies downwards causation. And this will be related to causality, that it's another limit because, let's say, we don't really have decent methods of studying causality. But anyway, we can say that in general, emergence is information that is not present at one scale, but it is at another scale. And another concept is that of self-organization. We can say that a system can be usefully described as self-organizing, where we have global patterns that are a product of the interactions of the components. And another limit that we have is that of computability. That of course, we should further distinguish computability in theory, which was defined by Turing, precisely to prove the undecidability of formal systems, and computability in practice, which is basically that we can have a computer finishing infinite time something, because Turing machine has infinite memory and infinite time. So we can have functions that are Turing computable, but we don't have enough time in the universe to actually calculate. And then there are non-computable functions that if we cheat a bit, we can actually compute. So you might have heard about this idea that if we have some monkeys on typewriters and we let them enough time, then they will end up producing the complete works of Shakespeare. So my daughter likes theater a lot, and then just for fun, I told her, well, let's just calculate how long would that be. Not for complete works, just first page of Hamlet. Okay, 500 characters. So let's assume that we have the fastest supercomputers so far, running from the Big Bang until today. How many characters would it have? 17. So, I mean, it will never finish just the first page. So, I mean, this is just to illustrate that combinatorics limits how much can we say about many systems, because we cannot explore fully all their state spaces. And in many cases, we act as if, let's say, we just need enough computational power or enough time, and then we'll be able to do it. And in networks, it's very often the case that whatever model we are using, it explodes exponentially or super exponentially. And then, let's say, what we can say about this is limited in the sense that we cannot explore completely state spaces, for example. So, for example, most of all possible chemical reactions will never occur. So if we wanted to build a network of all possible chemical reactions, it would always be incomplete, because there's not enough time in the universe to try them out. And of course, we can go this even further, which you might be familiar with this essay by Wigner on the unreasonable effectiveness of mathematics in the natural sciences, which actually, it makes one wonder, well, how come we have so many methods that actually work if, let's say, we can explore only a tiny space of all possibilities that, let's say, we can imagine. Let's say all the possible configurations of matter will never be instantiated. How come with such a tiny region of the state space we can evolve complexity and find so many things? So what are the regularities? So that another example, human genomes have, I don't know what's the latest number, because it goes down and devaluates, and now I don't know if to include the microbiome, but let's say 16,000 genes. So all the possible states of human genome would be 2 to the 16,000, assuming a Boolean idealization. And I mean, that's a huge number. So again, not enough time in the universe to explore all of those. But of course, human cells don't explore all possible configurations. So just with a few configurations, let's say, we are able to function and evolve and so on. So we can say that there are many more networks that we're able to describe completely than those that we can. And of course, doesn't mean that networks are not useful, but we should always doubt that we have full information. And also, even if we are sure that we have full information about one network, it might be that there is some change happening in the system, and then the network changes, or our representation of the system should be adapted. And then all the assumptions that we had might be updated or not. So relating network science, so one open question is how the network topology affects the classifiability that I mentioned briefly. So is it the case that, let's say, regular or random or scale-free like topologies, do they produce more or less classifiable data sets, or can we exploit the structure to increase the classifiability of data sets? That's an open question. And I mean, I mentioned that we have several limits of causality, that we don't understand it properly, difficult to distinguish from spurious correlations. When we speak about downward causation, if we speak to a physicist, they might say that it doesn't exist. If we speak to a biologist or a sociologist, they will say, well, of course, because, let's say, in a society, individuals define social norms, and then the social norms can promote or constrain behaviors in individuals. So basically, we need to model both scales, and we can easily describe causality at both scales. In some cases, even speaking about circular causality, even if it's at the same scale and we forget about upward or downward, can be problematic. And also, if we consider causality to be objective, then that might also be an error, because independently of an observer, there's no, let's say, causality between levels, because levels are a result of different descriptions that we have of phenomena, but let's say there is no difference between individuals and society independently of an observer. So let's say that's some artificial distinction that we impose on phenomena. So if we want to build causal networks of a system, we want them to be as objective as possible, but they will be of limited objectivity. How reliable can these descriptions be? Can we reproduce them? Can we verify them? Can we quantify them? So, I mean, all these seem to be open questions. And also, if we want to reconstruct networks, let's say we have some function, and then we want to reconstruct a network that produce that function. We can have an infinite number of networks that will fit that data, but then how to decide between all of those possible networks? And we might assume, oh, let's just follow Occam's razor and take the one that is simplest. But then, let's say, using Occam's razor might not always give the best solution, because, for example, if we want to fit a curve to some collection of points that we have, there might be a very simple curve that fits more or less the points, but it might make some errors as a more complicated compared to a more complicated curve. So let's say if we just take the simplest case, it might not be the most sharp. And I mean, of course, in science, we don't like to speak about subjectivity, but especially with networks, we need to do it, because at the end, networks is something that is defined by an observer within a context. And then depending on the context, we might have different representations for the same phenomena, depending on our purpose. And we won't have, let's say, one true network that will be the true description of a phenomenon, because it depends on what we're interested in describing. I mean, in philosophy, there's social constructivism, which basically says that reality, or what we would call reality, is socially constructed. So basically, we agree on what we decide is real, but it's not independent of a society. And it can vary from society to society. And of course, all the networks will be partially subjective, but we want them to be as objective as possible. But then how do we decide between different networks? It would be good to have like a recipe and say, okay, this level of objectivity is possible, and then we will be able to get it following these steps. So can we overcome these limits? Some of them not, because, for example, it's proven that you cannot go beyond the limits of formal systems. Even Gödel in his later years, he was still trying to prove the completeness of formal systems, but let's say himself, he proved that it's not possible. We have to be pretty much aware about the difference between the model and the modeled. As I mentioned, some people might see that these limits are a problem that should be solved, but actually they might be a feature in the sense that if we had access to absolute truths and to certainty, then there wouldn't be space for creativity, innovation, and serendipity. So maybe we should better embrace these limits. But then, of course, that would create more humility in us, but also would allow us to develop strategies that consider our own limitations. And of course, this has implications for how we're building artificial intelligence, and more generally, science and engineering. And it has some philosophical implications, but that would be another talk about the limits of philosophy. So just to summarize, better to accept and ignore limits of science. Can we break or accept them? And in networks, let's say this should be useful to go from structure to function and back, and lots of things to explore. So I take the opportunity to invite you precisely next year in Binghamton, less than 5 hours from here, conference on complex systems. We have great keynote speakers. And also, if you want to subscribe to Complexity Digest, you'll learn about the latest research and news that's going in the field. Thank you.
Questions? There were a bunch of questions already.
Okay, answers.
I have a question that is not specific on theory, but on your way of doing research. When you find a limit in research, how do you embrace it? Like, okay, you're working on something, so okay, this is something that it cannot be done. So how do you embrace it? You feel frustrated, or you try to find another way? Just a tips also for us that there are some you embrace limits in your research.
I mean, you try to go around it because, of course, you don't know at first whether you can overcome it or not, because it might be like, oh, I'm just being dumb, and I need to find the right solution. But then if you keep on exploring and then you understand why there is no solution, then you can start to find alternative explanations of what should be done. So let's say during my PhD that I was working with self-organizing systems as a way of coping with limited predictability that we have in non-stationary problems. One of the problems that I was working with was traffic light coordination. And their traditional approach is to optimize. But let's say when you try to optimize, you see that you will be very far from perfect. And well, first of all, I ended up defining what would be the theoretical optimum already when I was like having proposed several solutions. And then I wanted to compare my solution not only with traditional methods, but with the theoretical optima. So a posteriori, I can say that it's useful to try to find these theoretical optima so that you can know how far or close you are. Because if you're already very close, it means like, okay, this is the best you can do. But actually, in some other work that we did later, also with self-organizing systems, but for public transportation systems, the solution was better than the theoretical optima, which means that the theory was wrong, but that's a different story. But in many cases, it's a matter of keep on trying. But I mean, that's a feature of science, that we never have the final word, and you can always question what is considered to be the best solution. And then if you find something better, then it's good. But also being pragmatic, especially if you're doing your PhD, you need to finish with something. So whatever you have in many cases is good enough. I would say that I don't have like a general answer, oh, you should do this and that, because it's very highly specific what you should do in each circumstance. Because if you have limitations of time or budget, then even if you know that you are limited and that you might reach a solution or something better, then you don't have the time to explore it. And sometimes you do, and even you try, and then nothing comes out of it. But that's no reason for not trying. So because of course, if you do find something better, then that's what we do.
So you mentioned emergence, which is a phenomenon that appears in physics,
Mhm.
which is the Ising model. When you say there are limits, you mean limits about describing images?
Mhm.
Or, for instance, can you give an example of what those limits are?
Yeah, so there are several limits related to different flavors of emergence. So one of them is just accepting whether it exists or not. So some people don't believe that strong emergence exists, which would have downward causation.
Sorry, would you mind for
Yep.
explaining what downward and upward causation is?
Yes, so we can describe the world to be organized at different levels. So let's say atomic scale, chemical, biological, psychological, social, and so on. And of course, you can have intermediate scales in between. And in reductionism, people assume that if you have a complete description at the basic level, then you can predict everything that comes from it. So if it would be like a modern version of Laplace's demon, he said if higher creature would have access to all the positions and momenta of all particles in the universe, since they follow Newton's laws, this creature would be able to predict all future and to have access to all past because it's also reversible. And of course, because of dissipation, you cannot access the past because you have many states that go into the same state, so you don't know from where you come. So from thermodynamics, it was known that, let's say, such a demon wouldn't be able to get the past. And then about the future, there are many limitations that would prevent you to predict. One of them has to do with the information, well, with computational irreducibility, which is basically information that is not, let's say, at the moment where that demon had information. Other has to do with sensitivity to initial conditions and so on. But anyway, even when I think the most detailed simulations of elementary particles have, I don't know, maybe 40, 50 elementary particles and not more, because it's already too complicated. Still, people assume that you would be able to describe, I don't know, a human being, and let's say whether I decide to move my hand like this, that information is already encoded in the in my elementary particle somehow. So that's the only description we need. And then, of course, for convenience, then yeah, we can speak about physiology and electrical impulses, but that's necessary if you had that description at the lower level. And the idea of downward causation, which, let's say, I mean, can be also related with free will, is that if I say, okay, I will move my hand, then that would move the atoms in my arm. And if I don't have that description of let's say, language, then, I mean, since language has arbitrary meaning, if I don't have that description, then even if I had the full description of the atoms in my body, I wouldn't be able to predict that my atoms will move like this. So that's like these two opposing views, whether it's enough to describe going upwards or whether you need multiple descriptions to go up or down. And if we accept that, let's say, we need some subjectivity or also being pragmatic, one way of looking at this is with, I forgot the name of these functions that are used in cryptography. One-way functions, are they called? I forget. So they're functions that are very easy to calculate one way, but then to calculate the inverse, it's almost impossible. So that's one example of, I think it's one way. Yeah, one-way function. So for example, calculating the prime factors of a large number, it's very difficult with traditional computers, but doing the opposite, you just multiply the numbers and then you get a large number, and that it's very easy. So one way of interpreting this is that in some cases, in principle, you would be able to describe, let's say, from elementary particles what my hand will do or what my lips will do to express words, but it's in practice non-computable. So that's kind of.
Any questions? I have one that I promise I'll try to find a question, but it's just trying to help me classify some of this work. I think what I heard a lot of was like networks as descriptions and networks also as explanations, and there's maybe limits within each thrust of those two kind of umbrellas of the role in quant networks.
Yeah, so I mean, if we go to these different types of models, I think networks can be useful for different modeling purposes. So yeah, so
yeah, and this is helpful because it sort of classes the garden of fork and paths of like methods, limits, and development opportunities there. It sort of touched on this question. Is there anything like you're seeing as most sort of in today's world precedent for network science to resolve? Is one thing to kind of bound the space of what is and sort of is not possible, but then trying to find those gaps with actually.
Yeah. But I think networks are useful in all of these. I mean, they're one great way of studying complex systems or describing complex systems, because at the same time, you can represent elements and their interactions. And that's something that we didn't have until recently. And one of the reasons is because we don't have computational power to consider all the information required to describe and the elements and the interactions, let's say thousands or millions. So, I mean, right now I can think of something that's more salient than the others, because let's say each one can benefit from a network description. I guess if we manage to increase network literacy socially, then some of the implications of considering interactions as real will be easier to digest for the general public and for decision makers and politicians and so on. And let's say maybe that would lead to better decision making, in the sense that if we are aware that, let's say, one decision can have consequences because, let's say, their effects, let's say nothing is isolated, then that might lead to more cautious decisions in some ways, maybe. Maybe I'm too optimistic, yeah.
So I really like when you explain the concept that very configurations of matter, whatever we're describing, occur. Maybe more possible, but in the context of the way our society is building machine learning, trying to coin like from some perspective the concept of artificial intelligence. To what extent do you think we're cornering our future into a very similar scenarios that compared to what we have observed? So that's the first question. And the second one is, what would be the way out? Because throughout your talk, you said if we were able to make peace with this,
Yes.
maybe we could even use this
Yes.
as a better way to design things.
Yes.
And we have made a lot of mistakes, and yet machine learning tends to replicate
Yes.
past, right? So does that make sense? The question?
Yes, this is a great opportunity to make a shameless plug for my upcoming book about balance. We published by Oxford University Press next year. So I think that evolution in general is about balance, in the sense that you want to, there's a pressure of persisting or maintaining what you have already, but then there's also natural tendency to change, but then too much change is not desirable, and too much persistence is also not desirable. So I think that, because there are advantages and disadvantages to both extremes, and balance is where you have some change, but not everything is changing. So one of the difficulties of social transformation is that we have legacy that we are not willing to interrupt. So it's also a challenge, like if we want to renovate a railway system, but we need to keep the railways running, how do you, because it's very expensive to disrupt for a long time. It's a railway line, so then you keep on dragging the same technology for a long time. So in a similar way, our societies have many mechanisms that just to keep on functioning need to stay there. So we cannot just, hey, let's try something completely different, because we need society to continue. And the same is biology, in the sense that we carry many suboptimal legacy from our ancestors, but let's say biology cannot just start from scratch and, what if we put the lungs in a different way, or I don't know. But then, of course, with information and communication technologies, the change can be much faster and much more arbitrary. So in a way, we can explore new possibilities, and in some cases in a safer way, because let's say that's why we use simulations. But at the same time, the uncertainty is greater, in the sense that we might have an idea, this will be good, and then we explore all scenarios, and then there's something that we didn't consider in our model, and then let's say the consequence is very different than what we expected. But at the same time, I don't think we have much choice about it, in the sense that there's natural tendency, many natural tendencies that kind of continue progress in technology because of economics, because of many because of politics. So we won't be able to stop or change that immediately. But then within that restricted space, then maybe we can find new opportunities or new niches where, let's say, some things that right now we can't imagine can flourish, and maybe, let's say, as a proof of concept, that could be accepted and then propagate to other places. Because some people argue, well, we've never had so much abundance, so why there's still such a huge inequality? And the thing is that we haven't come up with an alternative to our economy where, let's say, which is still more industrial than informational. But then if we can show that there are new ways of playing the game, then maybe that would propagate if it offers more benefits.
Since you are data will just have a limited access to reality, in what way should we be careful when making claims about our reality through the models?
Yes. Yeah, I mean, indeed, we should always be aware, try to be aware that our models are limited. But at the end, it's the only thing we have. So it's not like, oh, they're limited, so then we cannot do anything. And they can be really powerful. But at the same time, we should always be aware that they're not absolute truths. Yeah.
Let's thank Carlos again. October next year, complex system or conference on complex system. Carlos is the president of the Complex System Society and has done a lot of work. I'm actually thinking about your answer about like public communication of a lot of these ideas. If you don't already follow Complexity Digest, just follow Complexity Digest and go to Binghamton for CCS.
Thank you. Today, yeah, tomorrow will be more automating.